Welcome back to the part 4 of lecture 2. In this part, we will try to understand the model, what we really mean by model complexity or the complexities of the models. Let us start with a very simple problem of our empty cars dataset. So on the x-axis, I have considered the horsepower, and the y-axis I have considered the miles per gallon. These are the points, and I have fitted a straight line regression miles per gallon equal to beta naught plus beta 1 times horsepower plus epsilon. The R square for this simple regression model is 0.602 and root mean square error is 3.74. Now what I can do, just looking at the visualization, we can feel like, okay, why not we try to fit a quadratic regression. So quadratic regression is miles per gallon equal to beta naught plus beta 1 times horsepower plus beta 2 horsepower square plus epsilon. So when I'm putting this horsepower square HP square as the third term, what is happening, I am effectively engineering this third dimension and putting the data which is actually in the 2 dimension into a three dimension, and this is sort of a behavior like that, and effectively we are trying to fit a hyperplane, a simple regression plane in the 3 dimension. Now when we are trying to do that, but actually what we are doing is we are trying to fit this, this quadratic curve. This purple color quadratic curve is our this curve, and from this curve we can compute the R square and root mean square error, which is root mean square error is 2.93 and R square is 0.756. Now one can say that, well, if I can fit a quadratic regression, I can fit a polynomial regression of degree 3 or order 3. So what will be that? That will be a miles per gallon equal to beta naught plus beta 1 horsepower plus beta 2 horsepower square plus beta 3 horsepower cube plus epsilon. Now you see, we can, now it is in the 4 dimension. We cannot draw 4 dimension thing, but effectively we are trying, the data now is being put into a 4 dimension geometry, and we are trying to fit a 3 dimension hyperplane on the 4 dimension geometry. By doing so, what we are doing is we are trying to fit this cubic line, which is represented as a blue. If you carefully look, there is also a purple line which represents the quadratic regression. So, and the R square for this polynomial of order 3 is 0.761 and root mean square error is 2.903. Now if you look into the three models, the first model is simple regression, linear regression. The second model is quadratic regression, and the third model is um, a model of polynomial regression with order 3 or degree 3. Now as I'm increasing the, but this was in a 2 dimension plane, this was in a 3 dimension plane, and this was not 3 dimension plane, this was a 3 dimension cube or 3 dimension geometry, and this model 3 was in a 4 dimension geometry where we fit a 3 dimension hyperplane. Now as we are putting more and more engineered features, I am putting it into higher and higher dimension geometry. My data, I am putting it into higher and higher dimension geometry, and so in that sense the model is becoming complex. My R square is going up, which is a good news. My RMSE is going down, but I am losing something. What am I losing? I am losing the interpretability. If I keep increasing the model complexity, what I mean by that, if I can fit a polynomial regression of order 3, I can fit a polynomial regression of order 5, I can fit a polynomial regression of order 7, I can fit a polynomial regression of order 10. I can fit as high complex model as one. So if I'm fitting a polynomial regression of order 10, that means effectively a two-dimensional data, I am putting it into a 10-dimensional geometry, trying to fit a 9-dimensional hyperplane. Of course, it's such a complex model, it will give me a very high R square, probably zero point 0.9 or 0.95 or 0.99, something like that. And RMSE will be very low. Um, but can we really explain that? This will be such a complex model, it will be very difficult to explain to the general public. It will be very difficult to explain your higher management and in a greater academic community. So with a very high complex model, we often lose the what is called model interpretability. So if I explain that model in simple terms, if the model become very complex, we cannot explain the model to a mass greater community. If you cannot explain your model to a greater community, it could be a very good model from the prediction purpose, but it will become sort of a black box model. And when it becomes a black box model, in a greater sense, it can cause some ethical issues as well, which we will discuss in later in the course. So, if we look into this model complexity, say in the first model is model of miles per gallon, beta naught plus beta 1 horsepower plus epsilon. Second model, the first model was a regression line in a two dimension when the data is in two dimension. The second model is a regression plane when the data one particular dimension is being engineered and the two-dimension data is being put it into a three-dimension geometry, and the regression plane is being used to model the data. Regression, now the third model, which is a polynomial of order 3, which is basically model the data is being put into a four-dimension model, four-dimension geometry, and we have tried to fit a three-dimension hyperplane in the four-dimension geometry. Or you can try some other features like horsepower, weight, and displacement as the other features, and so now actually your data is in four dimension and you are trying to fit a three-dimension hyperplane. But no matter what you does, it is as you put more features or more engineered features, your model or your data set is in a very high dimension. It's getting in a higher and higher dimension, and you're fitting a model at a very high dimension. Explain the model becomes harder and harder. That means model become much more complex. So the higher order regression with high model complexity. So the terms for curvature in linear regression, basically yi equal to beta naught plus beta 1 xi plus beta 2 xi square. Beta p xi p is polynomial of order p. If you can use sine cosine functions of increasing frequencies, and like y equal to beta 1 plus beta 2 sine omega xi plus beta 3 cos omega xi, and that kind of thing. Such models are known as Fourier model. So you can try these kind of models as well. The simple least square method can be adopted for any model which is linear in parameters. As I said, that if you go back this model, If you look into this model is linear in parameter as long as omega is known to you. But if omega is not known to you and omega is one of the parameter in your parameter space, then Fourier model is not anymore linear in parameter. You cannot apply a simple least square technique to estimate all the parameters including omega. So you have to, if you know omega, then sine omega xi you know, this thing you know, and then if you know omega, value of omega, then you know cos omega xi, the value of cos omega xi, you know this feature, no problem. Then if you know sine 2 omega, then you know what is the value of sine 2 omega xi given the value of xi. Then this model is linear in parameter. But if you don't know omega, the value of omega, and you want to estimate the omega using the data, then certainly we cannot say this Fourier model is a model linear in parameter. It is a non-linear in parameter. So we will not be able, if omega is unknown, we will not be able to use least square technique to estimate the parameters, because the model is not anymore linear in parameter. It's a highly non-linear in parameter. This is what we really say, that simple least square method can be adopted for any model as long as the model is linear in parameter. As p the number of predictors or the order of the polynomial increases, the model complexity increases. What happens when the model complexity increases too much? In order to find the answer for this question, first we try to understand two concepts: bias and variance. Let us try to understand what is bias. If theta is an unknown parameter and theta hat is an estimator of theta, then expected value of theta hat equal to theta plus b. If you can show that, then b is known as bias of theta hat. And if b is 0, then theta hat is known as unbiased estimator of theta. Now what is variance? Variance of theta hat is basically expected value of theta hat minus expected value of theta hat square. Now consider the prediction of a new response at x naught. Say y naught equal to f of x naught plus epsilon naught. Now, so you want to estimate f of x naught. That is what we are trying. So how are you estimating f of x naught? Your estimator of f of x naught is x naught transpose beta hat. We can say that x naught transpose beta hat is an estimator of x naught transpose beta. Beta is unknown parameter, x naught is known. So x naught transpose beta is some linear combinations of the parameters. So I can say x naught transpose beta hat is an estimator of x naught transpose beta. Since x naught transpose beta hat is an estimator of x naught transpose beta, it will have a bias and variance. But what does it mean in terms of prediction? Because remember that we are effectively want to build predictive models. Let's look into this miles per gallon data set. We want to predict miles per gallon based on the horsepower. Suppose for x naught value is 150. Now actual value f of x naught is this red spot, and this is the blue spot, which is the predicted value. This blue spot is the predicted value. So this difference we can say is the bias, and this very high variability, this is the very high variability. That means basically we are saying that okay, any value between this range could be a possible value. We can create using the variance or standard deviation or standard error of the estimator. We can compute a confidence interval. So this gives us the variability of our estimator. So this is an example of high bias with a high variance. Now, if you look into this situation, what happened? Here, still my bias is very high, but we have able to reduce variance as less as possible. So this is an example of high bias, low variance. Now, this could be an example of low bias and high variance because you see that our predictive power, the blue one, which is a predicted value, is very close to the true value, the red one, and so bias is less, but there are too much variability. So, and this is probably the best scenario in terms of low bias and low variability. So we will always look for something like this, with the low bias and low variability. It is very difficult to achieve, but we will look for that. So that brings us to the concept of what is called bias and variance trade-off. Consider the prediction problem or the concept of a new response input for x naught. So y naught equal to f of x naught plus epsilon naught. So I want to estimate this f of x naught, which is x naught transpose beta, and f hat of x naught is x naught transpose beta hat, is an estimator of x naught transpose beta. Now, if I know this is the estimator, I can compute the mean square error. So what is the mean square error of x naught transpose beta, which is basically y naught hat minus f of x naught, and we can invoke expected value of y naught hat as a minus and plus, and then apply a minus b whole square formula. We can split it up and we can say expected value of y naught hat minus expected value of y naught hat square plus expected value of y naught hat minus f of x naught whole square. So this is the variance of y naught and this is the bias square. So I can write mean square error as a function of variance of x naught beta naught hat and of that estimator and the bias. Now, typically what happens if you try to reduce the bias too much, your variance increases. If you try to reduce the variance, your bias increases. That is what happens. If you have a very simple model, what happens is, so my black one here is the mean square error. Remember that mean square error is the bias plus variance, bias square plus variance, that will give me the mean square error. Now, if my model complexity is too less, simple model, what happens that with a simple model may have a very high bias, but maybe a too low a variance. Then as the model complexity increases, the bias reduces significantly. As a result, mean square error drops. And after a while, what happens is your variance start increasing, whereas your bias vanishes because you have a very complex model. Almost you try to model everything you want. As a result, you reduce your bias to a significant amount, but as a result your variability increases, and as a result mean square error increases. So we don't want too complex a model, we don't want too parsimonious or too simple model as well. We want somewhere some parsimonious model in a sense which has a reasonable prediction power in terms of reducing mean square error, as well as which we can explain reasonably well to the greater academic community, corporate community, industry as a whole, everybody as a community. In the next part of this lecture, we will discuss the technique of variable selection, also known as feature selection, to achieve a parsimonious model with reasonable complexity. Please watching these video lectures. Please continue. Thank you very much.